This is pre-calculus notes on section 1.6, which is called geometric sequences. And this is the first set of notes on recursive form of a geometric function and graph a geometric function. The student objective is students will be able to find a common ratio. And then we have the definition of geometric sequence, which is when you multiply the previous term by a common ratio to get the next term. So I want to point out we've gone from arithmetic, which was adding a common difference. Geometric is multiplying a common ratio. Geometric means we're multiplying. Okay? And the number that we're multiplying by is called the common ratio. Okay, so we've got an example problem. Is the sequence geometric? And if so, what is the common ratio? Okay, so I've got a problem here. Is the sequence geometric? If so, what is the common ratio? So we want to look to see, is there a number that I multiply with each term to get each next term? So what can I multiply with 5 that makes 10 is 2. What can I multiply with 10 that makes 20 is 2. What can I multiply with 20 that makes 40 is 2. And so yes, this is geometric. And then the common ratio, which we designate with the letter R, is 2. Okay, so now, just like we came up with an arithmetic, a recursive form for arithmetic sequences, we have a recursive form with geometric sequences. So here our objective is students will be able to write a geometric sequence recursively. All right, so we've got a formula for recursive form of a geometric sequence. There's a formula, and what that says is that if I want to find each term in the sequence, u sub n, I'm going to take the common ratio and multiply that by the previous term. Well, that makes sense because of how we've just defined geometric sequence. All right, so here's that same sequence we had on the previous slide. And I want to now write or define this sequence recursively. So I'm going to do my u sub 1, state the first term. U sub n is equal to the common difference, which we already said is 2, times u sub n minus 1. And then the domain is all n greater than or equal to 2. Okay, so now we've got a sequence with all of these fractions in it. And whereas with the whole numbers, we could very quickly identify what the common ratio was here. Here, it might not be quite as easy. And so I'm asking myself, what can I multiply with the first term to make the second term? Well, one of the ways to figure that out, if it's not very obvious, is to take the second term and divide it. We're doing the opposite operation. Divide it by the first term. So if I were to take 7/9 and divide that by 7/3, well, you have to remember how to divide fractions. It's the same as multiplying by the reciprocal. So 7/9 times 3/7. You can cross cancel before you multiply. 7 cancels. 3 comes out of top and bottom. And I've got a common ratio of 1/3. All right, well, all I did was look at the second and first terms. I haven't really taken a look at the next two terms to verify that that's true. So I'm going to do that over here. If I take 7/9 and multiply that by 1/3, top times top, bottom times bottom, I get 7/27. Okay, that's right. How about if I take 7/27 and multiply that by 1/3? I get 7/81. So yes, this is a geometric sequence, and the common difference is 1/3. Okay, so write the recursive form of the geometric sequence. My u sub 1 is 7/3. My u sub n is equal to 1/3 times the previous term, and this is for all n greater than or equal to 2. Okay, new problem. For a geometric sequence with u sub 1 equals 3 and u sub 2 equals 6, find the common ratio. So you can ask yourself, what do you multiply by? Or you could divide, okay? So 6 divided by 3 is 2. The common ratio is 2. List the first 5 terms of the sequence. Well, the first 2 are given. And then we're multiplying 6 by 2, 12 by 2, and 24 by 2. And write the sequence as a recursive function. So I've got u sub 1 equals 3, u sub n equals the common ratio times the previous term for all n greater than or equal to 2. Here I've got that exact same sequence, and I'm going to take a look at the graph. Now, obviously I've got to get 48 on my graph, and I've only got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks. So let me count by 5s on the y-axis. For these things, you have to be able to determine how to label your axes to make stuff fit. Okay, so the x-axis is just going to be counting by 1s because I only have 1, 2, 3, 4, 5 terms. Okay, so the first term is 3. The second term is 6. The third term is 12. The fourth term is 24, and the fifth term is 48. Okay, this is definitely not linear. Remember that arithmetic sequences had linear graphs. This is exponential. Okay, geometric sequences have exponential graphs. Okay, that's it for the first video in this sequence of 1.6.